So, section F, continuity. So the function y equals f of x is continuous at x equals c if f of c exists, if the limit of as x tends to c of f of x exists as well, and if the two are equal to each other. So, there are different kinds of continuous functions. One kind is rational functions. Rational functions are continuous for their entire domains. So if this is what we were looking at, then it would be continuous everywhere except for when q of x is equal to 0. So when it's not equal to 0, it's continuous. Then absolute value functions also tend to be continuous. The graph of the absolute value of x looks like this, and it is continuous everywhere. Trigonometric and their inverse functions are also continuous everywhere, like the graph of sine of x would be like all over the place, and there's nowhere where it doesn't exist. Also, exponential functions and logarithmic ones as well. So y equals e to the x looks like that, always continuous. And then y equals ln of x is also continuous. Root functions are continuous everywhere, so like that. So like the square root of x, so y equals the square root of x. It's like this. It's continuous everywhere in their domain. So it's not continuous here, but that's not in its domain, so it doesn't matter. Okay. Now we're going to go to types of discontinuities. Right here we have a graph of f of x. It's like a piecewise function, and it has holes, and everything's not matching up. So it's not continuous everywhere. It is continuous at points like x equals -1, and at x equals 3, and at x equals 1. But there are three different kinds of discontinuities. There are jump discontinuities, there are removable discontinuities, and there are infinite discontinuities. Okay? A jump discontinuity would be at x equals 0, because the limit as x tends to 0 from the right side of f of x is equal to, if you look at it, it tends to 0. And the limit as x tends to 0 from the other side of f of x goes to 1. So they missed. So it's a jump discontinuity right there. Removable discontinuity would be at x equals 2, because it tends to, f of x tends to the same point from either side. However, f of 2 actually equals 0 instead of the expected -2. So the limit as x tends to 2 of f of x is equal to -2, but f of 2 actually equals 0. So that's a removable discontinuity. Infinite discontinuities means there's like a vertical asymptote there. That would be occurring at x equals -2, because there's a hole in the line, and there's no like dot like there is over here to fill that in. So that's an infinite discontinuity at x equals -2. Alright, and now, lastly, we're going to go over the theorems on continuous functions. The extreme value theorem says that if f is continuous on a closed interval AB, then f attains a minimum value and a maximum value somewhere in that interval. Which means we've got A, we've got B, and here's f of x, right? In this interval, from here to here, it reaches a maximum and a minimum somewhere in there. Doesn't matter what the function looks like. Okay, the intermediate value theorem says that for every continuous function, there is a point that is in the middle, intermediate, right there. So if C is right there, and this is f of A and f of B, then here's the midpoint, right in the middle. And the continuous functions theorem is saying that if f and g are both continuous, then any variation of f and g is continuous. So if you have f multiplied by a constant, it's continuous. If you have f plus or minus g, it's continuous. If you have f times g or f over g, it's also going to be continuous, provided that g does not equal 0.